let's take a look at a different central limit theorem problem. The National Retail Federation commissioned a national survey in November of 2009. A random sample of American adults were asked about their Christmas shopping behavior on Thanksgiving weekend. Among the 2,597, underline that, I have a feeling it's going to be important, respondents who said that they had done some Christmas shopping that weekend, the average amount spent, that looks like it's also going to be an important thing, was reported to be $343.31. Is 343.31 a parameter or a statistic? Well, I'm thinking that 343.31 is a statistic because it comes from the sample of 2,597. It's not the average of all American adults. So it's a statistic, and it's the average amount spent. So is that a categorical variable, or is that a quantitative variable? Well, that is a quantitative variable. It is not categorical. It's quantitative. It's money, and it goes, it's continuous. So that means that is our x bar, or I frequently use y bar. So x bar is equal to 343.31. Now, what is the parameter of interest for this study? Well, the parameter of interest for this study, that is, what is the number that we're looking for? What is the number that we're interested in finding out for the whole population? Well, that would be the average mean amount spent on Christmas shopping on Thanksgiving weekend. Now, I also have to say, well, what population does that represent? Now, when I looked at this problem, I thought that the population were the American adults, but not just American adults in general, the American adults that had done some Christmas shopping that weekend. The book says just American adults, but I kind of don't agree with the book. I think it's the American adults who had done some Christmas shopping that weekend, because there might have been a lot of American adults that didn't do any Christmas shopping that weekend, and I doubt that their zero spent was part of this 343.31. So that's kind of my take on it. So it says, let mu denote the mean dollar amount spent on Christmas gifts that weekend in the population of all American Christmas shoppers. Now they're kind of going along with my choice, right? And let sigma represent the standard deviation of those amounts in the population. Does mu necessarily equal 343.31? And 343.31 is our x bar. It is a statistic. It comes from a specific sample. We don't really know what mu is. I mean, the population is too large. There's no way we could really actually find it exactly. Is it possible that the survey obtained a sample mean of 343.31, even if mu was really equal to 350? What if mu was 400? What if mu was 600? Is it possible that we would have gotten this sample mean? Yeah, absolutely, it's possible. Now, whether it's likely or not is something that I think we're going to get into in this problem, but it's definitely possible. I mean, it's pretty close to 350, not that far away from 400, pretty far away from 600, but then it could be just like a random fluke. So it's absolutely possible that that could be the case. All right, so they want to give us some information. They're saying assume for now that mu is 350, and that the standard deviation, this is for the whole population, which generally means a sample size of 1. You know, you're taking one random person out of the entire population. You're taking another random person out of the entire population. So when you're looking at something like this for the entire population, n is usually equal to 1. And they're saying that the standard deviation is 150. So they want me to sketch the sampling distribution for the sample mean that is specified by the central limit. Well, first of all, quantitative variable is n greater than or equal to 30. Yeah, it certainly is. So our n is 2597. So our sample size is plenty big enough. And we know that our distribution of sample means is going to be normally shaped, unimodal and symmetric. We know that the mean of it is going to be 350, because that's what they told us. That's our mu. And we have to calculate our standard deviation. Since it's a quantitative variable, the standard deviation is sigma, our standard deviation of the population, divided by the square root of n. So that is going to be 150 divided by the square root of 2597. So that is equal to 2.94. Get the calculation over there on the calculator. Why is it reasonable to assume a normal shape to the sketch, even without knowing the shape of the distribution of expenditures in the population? That goes back to because our n is greater than or equal to 30. We have a plenty big enough sample size. All right, so it says calculate a z-score for a value of 343.31. That is our sample in this sampling distribution. Well, z equals y minus yr over s. So it's going to equal 343.31 minus, well, remember I use x bar, y bar kind of interchangeably, minus 350. That's our mean right here. That's our mu, divided by our standard deviation, 2.94. So we have a z-score of negative 2. We'll call it 2.28. So based on that, is it surprising that we got this sample mean of our 2,500 plus shoppers of 343.31 when the population mean equals 350 and the population standard deviation is equal to 1? Well, 2.28, that's a pretty low z-score. I mean, we know it's even outside the range of our empirical rule of 95% of the data. But we could calculate what the probability that is pretty easily, since we already have the z-score. I'm just going to go second distribution. I'm going to go normal CDM. Now we're looking for probability that here's my mean. Here's 343.31. The probability is that it'd be that or less. So I'm going to go negative 99, and I'm going to put in my z-score, my right boundary of negative 0.228. I'm sorry, negative 2.28. I'll close my parentheses, and I find out, yeah, it's like just a little over a 1% chance that I would have gotten that random average. So like a 1.13% chance. That's a pretty low probability. Well, how about if I, instead of figuring that the mean of the population was 350, I assume that it was 340. And I'm guessing that they want me to keep the same standard deviation of 150. Well, so let's, I have to calculate the new standard deviation. Or do what? I know that the standard deviation I'm looking for is going to be equal to the standard deviation of the population divided by the square root of n, well, that's the same as it was before. The standard deviation of the population is 150. The n remains at 2597. So my standard deviation is still going to be 2.94. Well, let's then take a look at the z-score for that. So I'm going to have, let's see the different color. I'm going to have z equals 343.31 minus 340 divided by 2.94. Well, 343.31 minus 340 divided by 2.94. Well, that's a much more likely probability. That is a z-score of, so z is going to equal 1.13. So if I found out the probability of that, I'm trying to find then the probability, I'm going to write over here. Now this is now 340. Here is my 343.31. So I'm looking for the probability that I would have at least 343.31. So I'm looking for that or greater. So I go back to my calculator. I'm going to go second distribution, normal CDF. I'm going to put in my z-score of 1.13, comma 99. Well, there's like almost a 13% chance that that would be that I get 343.31 or greater. So that's much more likely than like 1.13% chance of getting 343 or less when I got a higher assumed mean. So I'm not going to actually work the numbers for part J, but I'm going to talk about it a little bit. So it says suggest and justify another possible value of mu, so an assumed value of mu, that I would consider plausible for the population mean based on my observation that for my 2597 sample size, my mean was 343.31. Well, I mean, a really plausible mean would be 343.31. I mean, that would be exactly right on the money there. Anything relatively close to that mean, considering that my standard deviation is 2.94, is really pretty plausible. I mean, something that is not plausible will not be something farther away from the mean, like, I don't know, like $500. That's way too far away from the mean. It'd be highly unlikely that I would get this 343.31. Now it says, assuming that I didn't know the value of mu, so I don't know what the value of mu is, and I don't. But we know the standard deviation of the sampling distribution of the sample means from the central limit theorem because we know that this is equal to 2.94. How close to the population mean do we expect the sample mean to fall? Hint. Apply the empirical rule. What is true about 95% of the sample means? Well, now this is very interesting. And also very important. Because what it's saying here is I know I have a normal distribution, and I know I have some mean. I know that my standard deviation is 2.94. And I know that here's my mean, here's one standard deviation, here's two standard deviations, here's -1, here's -2. I know that 95% of all the possible values that I might get when I take a sample of 2,597 are going to be within two standard deviations of the mean. So 2.94 times 2, what is that? 8, 18, 588. So I can be plus $5.88, or I can be minus $5.88. And whatever that mean is going to be, whatever that mu is, that would cover 95% of all the possible values of my sample of 2597, with an n equal to 2597. This is an introduction to the concept of statistical confidence. Although I can't use a sample statistic to determine a population parameter exactly, I can be reasonably confident that the sample statistic falls within a certain distance of the population parameter. That's what we found right here. We calculated, the standard deviation based on the central limit theorem, and we can be 95% confident that the population parameter is going to fall within these two numbers here. The mean plus those two numbers. So once I observe the value of a sample statistic, I can be confident that the population parameter is within that distance of the sample statistic. So the distance depends on how confident you want to be on the size of the sample. The size of the sample, that led us to the standard deviation that we're going to use. How confident we want to be, we determine that by, well, if we want to have 98, 95% confidence, we use two standard deviations. If we only wanted to be 68% confident, to get closer to the mean, well, then we would use one standard deviation to calculate our distance from the mean. So this concept of statistical significance, this is going to come up a lot more when we talk about confidence intervals.